Hello, viewers. Today I want to talk about two papers in the realm of pruning neural networks. The first one is optimal brain damage, also known as OBD. And the second one builds on top of this is called optimal brain surgeon, OBS. So these two papers come from around 1990s, and they're fundamental in the ideas of pruning neural networks. So I just want to give high-level overview of each of them and then go into kind of the math details behind them. So I'll start with optimal brain damage and then I'll move on to optimal brain surgeon after. So the fundamental problem in machine learning that these papers try to work on is the performance complexity trade-off. This is also widely known as bias variance trade-off. And that's the idea that if you have too complex of a model, it won't generalize well to new data, right? Because if it's too complex, it will fit the training data very well to the point where it's specific to the training data, and it won't be good with new data. So that's a model that doesn't generalize well, and that's on the side of complexity and variance. If a model is too simple, then it won't model whatever it is you want to model well, both the training data and the test data. It'd just be too simple to be powerful. And kind of a long-standing way of addressing this is by adding a complexity term in the objective. So we have our normal loss term there. So if we measure the data fitness of the model, and then we add a penalty for being too complex, whatever complexity term we want to use. And then we add a hyperparameter to control how much we want to penalize for complexity. So that's just background. The paper didn't really go into this, but that's just something good to know. But what this paper assumes is that models with more weights are more complex, and models with less weights are therefore less complex. So if we remove weights or parameters from a model, then we're going to move it towards simpler. We're going to move it towards generalizing better. And neural networks have been known to be on the complex side, high variance side, where they can fit data very well, and therefore they're more likely to overfit. They're more likely to not generalize well without specific techniques to avoid that. So with the neural network, you usually start on the high variance side and you try to move it towards more bias. And that's what this paper tries to do. And it does that by pruning. So you have a very strong neural network, and then you remove weights so that it becomes less complex and therefore generalizes better. So that's what pruning is. And the main thing we need to solve is, well, which parameters to prune. But let's just assume we know what parameters are unimportant. How do we apply the pruning? Well, there's one thing known as hard magnitude pruning versus soft magnitude pruning. And that's just the idea that we could either set the weight to zero or we can just make it close to non-zero or reduce it significantly, but it's still not zero. So, for example, let's say we know a weight is unimportant and has a value of 10. With hard magnitude pruning, we would move this to 0. With soft magnitude pruning, we could do something like reduce to like 10% of whatever its value is, or however we want to apply it, but we just don't zero it out, and that would make it 1. So that's hard magnitude pruning versus soft magnitude pruning. Now, when we prune a weight, so let's just say we zero out a weight that's 10, now it's 0. Well, we need to adjust the rest of the parameters to to it to compensate for that 0. So how do we do that? We can either retrain the model completely, even allow the weight that we completely zeroed out to be retrained, or we can freeze that weight that we zeroed out or dramatically decreased, however you want to apply it, and it won't be allowed to move around. So that's the idea of hard pruning versus soft pruning. So that's assuming we already know which weights to prune. So now the question is, well, what weights do we prune? So before we get into that, just quick summary. Benefits of pruning are better generalization because you move the model towards something more generalizable, something more simple. Sample efficiency is better because you have less weights, so you need less training data to train your model. And because you have less weights, you also have improved training and inference speed. So training will be faster and inference will also be faster. So that brings us to our question again. Which parameters should we prune in a neural network? There are some models where it's clear which parameters we should prune. So for example, polynomial regression, we have y equals first parameter times x plus second parameter x squared plus third parameter x3 and so on and so forth, right? With a model like this, we would prune the higher order terms first because they capture less of the general trend, the generalizable part of the data, and they capture more of the fine-grained trends and details of the data, which would lead to a model that's more complex and less generalizable to new data. So we would remove higher order terms first. But with a neural network, it's less clear which parameters we would remove. So this question is what this paper, OBD, optimal brain damage, addresses, as well as optimal brain surgeon. Which parameters should we remove in a neural network? Prior to optimal brain damage, most of the pruning work revolved around magnitude-based pruning, which is the idea that the smaller the parameter, the less important it is. So we remove the smallest parameters first. But with OBD, it states that this is not necessarily correct because a parameter might be small, but still be important to the objective, right? So let's say we have a parameter theta 1, right? Let's say we have a parameter theta 2. And let's say we have an error, also known as the objective function in this case. So let's say we're fully trained. We have 2 parameters, theta 1, theta 2, and we have a converged error function. So which parameter should we remove, 1 or 2? And knowing that we can measure E. Well, we want to remove the one where if we remove it, the error goes up the least. The objective stays as good as it can. And notice this doesn't really involve the size of the parameters, the magnitude. It might be correlated somehow underneath everything, but just based off this example here, we don't know that removing the smallest one is the best idea. So that's the problem with magnitude based. There's no really proof behind that being the best option. So, and saliency is a parameter's importance to the objective, and that's what we want to measure for each parameter. Therefore, we remove the parameters that have the least saliency, the least importance. So now we move on to what OBD addresses. So magnitude-based pruning is not conceptually accurate. And oh yeah, so there's a brute force way to measure saliency, which is just we remove one weight, retrain the model, see how the objective does, and then we put that weight back, remove another one, see how the objective does. So we just take turns removing one weight, measuring how the objective changes, and the one we ultimately remove is the one that has the least effect on the objective function, because that means it has the least saliency. That means it's the least important. So that's a brute force way to do it, which is an accurate way to remove a weight. But the problem with that is it's just infeasible computationally. So that's the current gap with previous work before optimal brain damage. And what optimal brain damage does is it introduces a efficient way of measuring saliency so that we have accurate decisions on the weights to remove while also not being computationally infeasible. So this is done by using the second order derivatives of the objective function. And with that, we could go into the math to explain a little bit more. But that's the main idea, is that we find the saliency of the weights with one being accurate and two being feasible. So the approach is we train a neural network until reasonable solution is obtained. We compute the second derivatives, which I'll show why it's relevant for the saliencies. And with the second derivatives, we can compute the saliencies of each parameter. Then we sort the parameters by saliency and just delete however many of the lower saliency parameters we want. So again, low saliency means unimportant to the objective function. And then we just iterate until we achieve a desired prune fraction, just a desired amount of weights removed. And another thing about the approach is that in the paper, they stated that they graphed the saliencies. So imagine you have all the saliency, you graph it kind of to see the saliency on a higher level. So maybe layer by layer, and then you can see if it's worth just removing an entire layer. Like imagine if all the saliencies in the last layer are very low, then it would point to maybe we don't need that last layer. So that's what they did. And the result, they removed up to 60% of parameters without changing performance. So that's pretty good. And they did that with this method. So with that, I want to go into the math now. So let's start with the Taylor series. Recall the Taylor series approximation looks like this. And why is this important? Well, we can apply it to our objective function and weights. So what the Taylor series does is it approximates where the value of an objective function at another point close to your current point. So if we apply this to the objective function and the weights, we can estimate how much the error function, objective function changes given that we move a little bit. And in this case, move a little bit means pruning one of the weights, right? Because if we can estimate how the objective function changes given that we remove a weight or reduce a weight, then we have a measure of that weight's saliency. So that's why we apply the Taylor series approximation to the objective function and the weights. So here is just that applied, and then we subtract this term here to have the change in the objective function or an estimate of them. And now we expand. So here the gradient, we just is this blue value here. We expand by component. And then we do the same with the Hessian. So the reason we do this is just so that we can apply some approximations um, later down the line. So here's our full estimate of the change in the objective function given that we change the weights. And now we apply some approximations. So the first one is quadratic approximation, and that's just the idea that we remove the third order and more terms from the Taylor series approximation. And this is just to be more feasible, but while keeping accuracy with the second order term. Okay, now extremal approximation. So we assume we already trained the model, and because of that, the model has converged. And because it converged, the gradient of the objective function is 0, right? If it wasn't 0, then we can still train to move it towards 0. So we assume it's somewhere close to 0. So because of that, we completely remove this term because this is the gradient of the objective function. Okay. So now we have just the middle term here expanded, the green one. Now we apply the diagonal approximation. So we completely remove the cross-term interactions in the Hessian, and we assume the Hessian only has values on the diagonal. So this is important because the later paper, Optimal Brain Surgeon, doesn't assume this. So that's the main difference between the two papers. But with that, now we have a measure of saliency. And what is it? Well, we could approximate how E changes, the objective function changes, given that we change the weights by delta W. And this we can compute. So that's all the math really behind optimal brain damage. And this is done with backpropagation. Okay, so now we're at optimal brain surgeon, and this builds on top of optimal brain damage. I would say that optimal brain damage is more fundamental, has more of the knowledge behind pruning because optimal brain surgeon builds on top of this, but it's basically the same idea. So let's go into it. So we start off at the same question. Which parameter should be pruned in a neural network? Okay, and the current gap is that OBD and magnitude pruning remove the wrong weights. So basically, OBS is trying to find an even more accurate way to estimate saliency other than the diagonal approximation. So that's the main difference, and it does that with using the inverse of the Hessian matrix. And we'll go over the math, but that's what it does. It's basically just more accurate, except more computationally intensive. So what's the approach? Well, similar approach, we train a network to minimum error. We compute the inverse of the Hessian, and we'll show why that's important. And then we find Q, which is just an index of the weights. So we find the parameter that gives the smallest saliency, basically. We remove it if it makes sense to, otherwise we stop. If it does make sense to remove it, we iterate, try to find another weight, see if it makes sense to remove that one, given that it has small saliency, so on and so forth. The difference with this compared to optimal brain damage is that we have all the saliencies in optimal brain damage and we just remove whatever amount we want. This one we remove one weight at a time and we update the weights. So that's another difference, is that once we remove a weight, we have a way to update all the other weights without retraining. Whereas optimal brain damage, we remove certain amount of weights and we retrain. This one, after we remove a weight, we don't have to retrain. We update all the weights mathematically, we'll show. So the main computationally intensive part in this approach is computing the inverse of the Hessian. And we don't assume diagonal approximation, so this would take having the full matrix. So what's the result? The main result is that we find the right weights to remove, whereas sometimes OBD and then also coarse magnitude pruning, we find the incorrect weights. So it's just accuracy. And then we'll go over the math, but main difference with OBS is accuracy of the weights to remove. But it does require more computation. So it's more of a theoretical foundation for other papers to come, because let's assume you're able to approximate this in a smart way. Well, then you have an accurate way of removing weights, and then you also improve the feasibility of this paper. So it is a fundamental, but by itself, I don't think it's practical. But yeah. So now we go into the math. So now let's go over the math of optimal brain surgery. So we start off very similarly to optimal brain damage. We start off with the Taylor series estimate of the change of the objective function, given that we change the weights a certain amount. So we also start off with the same approximations and cross out the first term, extremal approximation, and the third term, the terms of the Taylor series, the third order terms, and later of the Taylor series. So if we go back here, that's just these two. This is the quadratic approximation, and this is the extremal approximation. The only thing is that we don't apply the diagonal approximation. Again, this is done for more accuracy. But again, yeah, just for more accuracy, and we'll go through the math some more. So the difference with optimal brain surgeon is they take an optimization approach as opposed to just algebra and calculus. So what do we want to do if we take an optimization approach? So again, we're removing one weight completely. And given that we remove the weight completely, we want to minimize change in E, right? So we remove one weight completely. We removed it. Now let's minimize the increase in the error function. So that's what this whole line is saying. And we just need to convey this in math. We remove one weight completely. So how do we do that? Well, long story short, it can be written as this. This is the unit vector corresponding to the Q index dotted with the change in the W's, changing the weights, plus the WQ. That should equal 0. So this is just saying we remove one weight completely. And now we have our full constrained optimization problem. We can use the Lagrangian, and without going too fundamental, too back, the Lagrangian is just a way to solve constraint optimization problems where it abuses the idea that the main function and the constraint, the gradients will be pointing at the same direction at an optima. So if we set this gradient of L to 0, we can set the two equations with respect to the change in W and with respect to this coefficient here that we add, and there should be both equal to 0. So that's what we do. We start off with change in W. So this should be equal to 0. Then now we have our change in W. Okay, now we do it with respect to what's called a Lagrange multiplier. It's just this coefficient we added. And we get our Lagrange multiplier's value. Okay, now we just plug in here to here, get this, and it starts to get a little bit complicated, but we'll get to where we want to be. Okay, so now this change in W is the optimal change in W. And because this constraint was added in, we already assume one of the weights was completely deleted. So this is our optima change in W for this equation. Now what do we want to do? Well, we want to plug in change in W again, and we want to find L, right? Because this would be the change in the objective function, given that we remove the weight Q, just one weight. Okay, and then we adjust the other weights, but that's the saliency. So we plug it back in. We have this, plug it back in, we do some reductions, so on and so forth. And then we have our measure of saliency. That's the math of both optimal brain damage, optimal brain surgeon. The difference is optimal brain damage assumes the diagonal approximation here. And just we solve for saliency using backprop, whereas optimal brain surgeon, we require the inverse of the Hessian to compute the saliencies. So optimal brain damage is more feasible, but optimal brain surgeon is kind of more mathematically accurate. And if we can approximate the Hessian, the inverse of the Hessian with later methods, then we can accurately remove weights. So that's optimal brain damage, optimal brain surgeon. I hope I explained it well. I hope the math kind of made sense at a high level. So that's that, and hope you enjoyed learning about this today.